Hello, Dr. David Kriller here at the Department of Chemistry of Georgia Southern University. Here I am in this second video installment in this series that's going to teach about the chemistry of water. In the first video we talked about the autoionization of water, which set the stage for understanding of things like the fact that water always contains hydroniums and hydroxides in concentrations that are in equilibrium. And that understanding set the stage for our understanding of the pH scale. And then when we defined pH, we also defined pOH. And we saw that all these things, hydronium concentrations, hydroxides concentrations, pH and pOH, all these things could be interrelated. So here in this second video installment, we're going to talk about strong acids and bases, okay, specifically. We'll talk about their chemistry. We'll talk about them in terms of the amount that they react. And it's going to be a very simple concept. You know, we have talked about concepts of equilibrium. Well, for strong acids and bases, you really don't have to get as fancy as applying equilibrium concepts. You just understand that they react completely, or 100%. We'll do a couple sample calculations. You will see what we mean by that. Let's keep moving. So let's start by reviewing the autoionization of water, because it's so important and it's so foundational to everything else. We understand that two water molecules can react with each other, with one water molecule acting as a Bronsted-Lowry acid, the other reacting as a Bronsted-Lowry base. And so the products are hydronium and hydroxide. So we understand why water always contains these ions, and that it's an equilibrium process. And so there is an equilibrium constant, which we denote Kw, which is a small value, 1 times 10 to the negative 14. So pure water, water that has no impurities of any nature in there, it's just water, will always be creating hydroniums and hydroxides by this equilibrium that's innate to the substance. Those hydroniums and hydroxides will always be created in equal concentrations. If there's nothing else in there affecting the equilibrium, they will be present in concentrations of 10 to the negative 7 each. pH will be 7. However, of course, you know from the pH scale that there can be a wide range of concentrations of hydroniums and hydroxides, and associated a wide range of pH and pOH, as also we've defined. So how do you get into those solutions that are very acidic or basic? Well, a lot of people just know this language. To get an acidic solution, you just have to add an acid to the water. Or to get a basic solution, oops, that second line should say basic solution, but you know what I mean. Okay, well, there's two kinds of bases, two kinds of acids and bases generally, strong and weak. So let's first talk about strong acids and bases. And we're going to show you a list in a second here of common strong acids and bases that chemistry students need to memorize. Well, yet learning these is like learning vocabulary while you're in the process of learning a new language. However, it gets easier and easier to memorize chemistry vocabulary the more chemistry you understand. Don't worry about it. Just as you learn more, it'll get easier and easier. Okay, strong acids and bases are basically, I like to think of them as very ionic compounds that ionize or dissociate in solution, breaking up to produce ions. And acids or bases produce, as one of the ions that's formed, either hydroniums or hydroxides. So it's very simple chemistry. So here's a list of strong acids. Like I say, think of them as ionic compounds, where they're combinations of a cation, which is always the hydrogen, positively charged hydrogen ion, and an anion. So the first three on the list here, the anions are halides, and the last four are polyatomic anions. The strong bases are ionic compounds, and they're like salts, where the cation is the metal and the anion is the hydroxide ion. We'll talk about the interesting stoichiometry of the group 2A metal hydroxides, or equivalently the alkaline earth metal hydroxides. Let's talk about the chemistry. For strong acids, one of the dissociation products is the H plus ion, as I said. In its simplest representation, you could just say that, something like HCl breaks apart into ions, one of which is H plus and one of which is Cl minus. But, of course, we should be aware that the hydrogen ion is a very reactive species, and it's not just going to float around by itself. It's very reactive. and it's going to add to one of the many trillions of water molecules around it. So it just adds to a water molecule, and then that water molecule turns into a cation, H3O, the hydronium, which is then solvated by other water molecules around it. Okay. For strong bases, when it breaks apart into ions, one of the dissociation products is a hydroxide ion, such as here for sodium hydroxide. Okay, so let's do a couple calculations really fast. Okay, for the strong acids, and monoprotic means acids that can just give off a single hydrogen. The acid is going to react completely, 100%. When the acid reacts, it produces hydroniums. So it's going to react completely. So the concentration of hydroniums that you're going to end up with is just going to be like stoichiometry equal to the starting concentration of acid that you put into the water in the first place, because all the acid reacted completely. I'll just make a note here in passing that the astute chemistry student might say, well, if we're keeping track of hydronium ions, say if we're going on then to calculate pH, and we're adding up all the hydroniums, sure, the strong acid produces some hydroniums, but doesn't water itself produce hydroniums via the auto-ionization of water? Well, yes, I'm glad you asked. Yes, water does produce hydronium ions. So in principle, there is a second term to this. But if the concentration of acid is high enough, the concentration of hydronium ions that came from the acid will be so much higher than the concentration of hydronium ions that came from the water, you can ignore the hydronium ions that came from water. And that's the case when the concentration of strong acid is about 10 to the negative 6 molar or higher. Okay, so let's work through this one together. What is the pH of a 0.0200 mole per liter aqueous solution of hydrogen bromide? Well, let's remind ourselves the behavior of hydrogen bromide in water. So HBr will write it here, reacting with a water molecule, transferring a proton, since it's Bronsted-Lowry acid, after all, to the water molecule. So the water molecule turns into H3O+, and the other product is the bromide ion. We're going to calculate pH, so we need to know hydronium concentration. Well, if all the, whenever HBr reacts, and all of it will react, whenever any of this acid reacts, you see the hydronium ion and the bromide ion are created in one-to-one stoichiometry. So the concentration, so if this is the only acid in water that's creating this, these hydronium ions, the concentration of hydronium ions is going to be equal to the concentration of bromide ions, because they're formed in one-to-one stoichiometry. Because that HBr is a strong acid, all of it is going to react. The concentration of H3O, of hydronium ions that's created, is just equal to the initial concentration of the acid, which is 0.0200 mole per liter in this question. The question is asking what's the pH. Take the pH, to find the pH, take the negative log of the hydronium, which is 0.02. And that turns out to be 1.7. That's the answer to that one. So that's a relatively straightforward question. There might be another level of complexity. Some questions might go on to ask you, what's the pOH of this solution? But I'm sure you could handle that. So strong bases. Okay, again, react completely. So the concentration of hydroxide is just equal to the initial concentration of base. If that base is monobasic, i.e. like the hydroxide salts of the alkali metals. But if we're talking about dibasic bases, like the alkaline earth hydroxides, like barium hydroxide or calcium hydroxide or something like that, CaOH2, the concentration of hydroxide will be 2 times the initial concentration of base. Again, with the same note we'll make for people who are interested in knowing when it's okay to make this simplified assumption that the concentration of hydroxide is just going to be equal to the initial concentration of the base. Okay, so here's a question that we're going to work through together. What's the pH of a 0.015 mole per liter aqueous solution of barium hydroxide? Well, let's remember the ionic nature of barium hydroxide. Barium ions are Ba2+, hydroxide ions are OH1-. So of course, when you stick them together to form an ionic compound, it has the formula BaOH2. And when that dissolves, one equivalent of BaOH2 produces one equivalent of Ba2+, and 2 equivalents of hydroxide. The hydroxide ion concentration is going to be because of the stoichiometry here, because it's BaOH2, hydroxide ion concentration is going to be 2 times the concentration of barium ions, twice as many hydroxides formed as these ions, which these ions have twice the charge anyway. And the concentration of hydroxide is going to be 2 times the initial concentration of base, which is 0.015 mole per liter. So hydroxide ion concentration is 0.03. Well, we're asked to find pH, but because we have the hydroxide ion concentration here in front of us directly, let's go via pOH. Let's first calculate pOH. Negative log of 0.03 is 1.5. The pOH is very low. That's a very basic solution. What's the pH? Just 14 minus the pOH, that's 12.5, as you see from the pH. It's a very basic solution. So those are a couple questions that we just worked through, calculations for strong acids and strong bases. Things will get much more interesting on the next video segment when we talk about weak acids and weak bases. Okay, I'll see you in the next video segment.